All right, guys, what we're going to be doing today is learning about something called a critical value. Okay, so we need to make sure that we identify this as a vocabulary term that we're going to start using a little bit in the future. And we're going to be able to determine the exact value of any roots of a function, but we're not going to be using algebra to do this just yet. We're just going to find them by looking at a graph. And maybe that's going to mean graphing the function on a graphing calculator and using the features of the calculator to identify those roots directly. All right, so in this case, we've got a function. It's not defined what it's called. We could call it, let's just call it function f. Okay, so this is f. And I should probably detail that this function continues in both directions forever. It's not just bound to this grid that we're looking at. There should be arrows there probably. And if I'm talking about the roots of a function, this is probably not something that's new to anybody, but we should probably go back to the basics. The roots of a function are just going to be wherever that function touches the x-axis. So it wouldn't be a bad idea to maybe make a note of that. All right, so now that we remember that the roots are where our function touches the x-axis, we're going to take a look at our function here. And if I travel along this function, it looks like I cross the x-axis here. And it continues along. I cross the x-axis again, then finally a third time. Okay, so where are these 3 points? Well, the axes aren't labeled, so let's for now assume that it's counting by 1. So this would be at the point -4, 0. This would be at the point -1, 0. And this would be at the point 2, 0. So I'm just going to write those points in. -4, 0, -1, 0. And 2, 0. So if those are the 3 places where the function touches the x-axis, it's all right for us to say that our roots are at x equals -4, -1, and 2. And we also want to identify that roots are one of our critical values. So if I say, what are the critical values of a function, one of the things I'm referring to is the roots. I want to know where the roots are. The y-intercept, some people may think is a root, but it is not. The y-intercept is wherever your function touches the y-axis, so it's kind of like the roots for the y-axis, but we're not going to call them roots. So our function touches the y-intercept at this point right here, just one time, at the point 0, -2. So our y-intercept is at the point y equals -2. It's important for us to remember that that is not a root. It is also not a critical value. Maximums and minimums are exactly what they sound like. We can have 2 different types of maximums and minimums. We could have local maximums and minimums, and we could have absolute maximums and minimums. So I just want to talk a little bit about the difference there. This point right here would be what we would call a local maximum. The reason we call it a local maximum is because the function is increasing until that point. And then at that point, it begins decreasing. All right, so on either side of that function, all of the points are going to be less in value than this point, right? They're all lower. So because all the points surrounding that point have a lesser value, this is a maximum. But I don't want to call it an absolute maximum because it is not the absolute maximum value for this function. The reason for that is because if I keep going along the function, sure, it's increasing, we do hit a maximum here, but it's only a local maximum. And then we decrease for a while, and then we turn around again, which would make this point a local minimum. So I'm going to outline that point there to be a local minimum. And then if we continue on, you'll see that the function increases, it increases, and keeps increasing forever and ever and ever. Because it's increasing forever and ever and ever, we have a lot of points that are above the height of that maximum that we detailed from earlier. So I can't say that this is the absolute maximum of the function because I could tell you that there are a bunch of points over here that are much greater in value than that point. So how could that be the absolute maximum if this point here is even greater in value? But it is a local maximum. So let's take a second and define local maximum and absolute maximum as well as minimum. All right, so we have local extrema which just refers to extreme values, maximums and minimums, and we have absolute. All right, so local extrema are going to refer to just at one point in the graph, you must have points on either side of that point that are either all lesser or all greater than that point. All right, but if we're talking about an absolute, that means all other points are lesser or greater. Okay, so the key word here is all if we're talking about absolute. So we don't have absolute maximums or minimums in this particular case. I'm just going to zoom in. Hopefully that's helpful. We just have these 2 points that are local, and we don't really even know the values of those points. So just for our purposes today, I'm just going to call this the point A, B, and I'll call this the point C, D. So we just need to make sure we detail that we know where the maximums and minimums are. So our max, which is a local max, is at the point A, B, and our local min is at the point C, D. All right, one more thing that we want to talk about when we're looking at a function is the concavity of that function. Oh, and I'm sorry that I forgot to mention, maximums and minimums are critical values. So those are the only other 2 critical values we're going to talk about. If I'm mentioning critical values, I'm referring to roots, and I'm referring to all local maximums or minimums, any local extrema, this word here. All right, so the concavity of a function. Well, concavity might be a new vocabulary word for all of you, but it just refers to the direction that the function is bending. Okay, so if a function is concave up, then that means that the function is opening upward. So our function is opening upward in this space. All right, so this is an area where our function would be considered to be concave up. Now over here, our function is opening downward, so that would be concave down. At this point in Algebra 2, it's really just an intuitive thing. We don't need to define it too rigorously, but we do need to point out that concavity is referring to the direction that your function is opening. And this isn't going to be something we deal with a line, because a line is just straight. But when we do get into polynomials that curve, we will have portions of those polynomials that are concave down and portions of those polynomials that are concave up. So all I'm going to do right now is just to help us out here, I'll highlight the concave up portion in green. It looks like we're concave up from about here on. All right, and we are concave down in this region, it looks like. So I'm just kind of drawing all over my graph here. If you want to just circle those parts of the graphs, that's fine. We're not really going to get too deep into concavity, but you should be familiar with the term. The last thing we need to talk about in this video is domain and range. So when we're referring to the domain of a function, we're talking about the x values or the input values. And when we refer to the range, as you might guess, we're referring to the y values or the output values. And we know this from our last lesson. We talked about domain and range a little bit. You saw it in the function machine video. So I would ask, what is the domain of this function? What are the possible things that I could input into this function f of x? And you could just start thinking of examples for yourself. Could I put a 0 into this function? Yep, 0 is here on the x-axis, and if I put a 0 into this function, it looks like you get an output of -2. So I can put in a 0 into the function. Can I put a 2 in? Yes, if I put a 2 into my function, my output is 0. So 2 is also in the domain of the function. Can I put a 3? It looks like I can put a 3 into this function. I would have an output that's out here. And because this function continues forever and ever, I can keep picking any large value of x that is real and plug it into this function. And that's also true in the negative direction because the function continues forever and ever in the negative direction. So as far as the domain is concerned, there is no limit to the values that I can plug into this function. I could go all the way from -infinity all the way to +infinity. because all the way this direction, it's okay to plug in numbers, and all the way that direction, it's okay to plug in numbers. So one way to note that is by putting negative infinity to positive infinity in parentheses like that. The other thing I could say is because this contains every real number, I could just call this all real numbers, and that's the symbol for all real numbers. It's a double R. Now, when we talk about the range, we're talking about outputs. Okay, so what are we able to get out of this function? And it might be useful even to kind of turn your paper if you want to look at it this way. You want to think to yourself, can I get the number 3, for example? 3. So 3 is here on my y-axis. Is it possible for me to plug something into this function and get 3? Well, over here, it doesn't look like that's going to work. But over here, it does look like there is a value that I could plug into my function to give me 3. And if I did the same question with 4, yep, it looks like there's something I could plug in to give me 4. 5, there is a number that I could plug in that would give me 5. 6, 7, and you can see that this would go on forever and ever and ever if I'm traveling up the y-axis, because the function continues forever and ever. So there's no limit to what I can plug in to get numbers that are outputs that are extremely large. And that's actually true as we travel downwards as well. Could I get 2? Yeah, actually 1, 2, 3 values give me an output of 2, so we're good there. Same thing if I chose 0. There are inputs that give me an output of 0. And I could keep going very negative too. Negative 3. It looks like there's an output that gives me a negative 3. A negative 4, I would have one of those as well. So again, we're in a situation where we are not restricted when we're talking about the range. So the range of this function is also from negative infinity to positive infinity, because there is no limit to the outputs that I could get from this function. And of course, another way to write that is with the double R, all real numbers. So this is just some terminology that I kind of want to get out of the way before we come to class tomorrow. And in class, we'll start playing around with real functions with the graphing calculators and determining those critical values as well as their domain and range.